A similar approach can be taken when the system logic is a little more complicated, as we see here. The element E2, it appears twice in the block diagram, but obviously it's not twice present physically in the hardware. So this is one way of showing the role of the element E2 in the system logic. So we would proceed similarly as we did in the case of the bridge systems. If you want to work through this, please go ahead. Otherwise, let me present the solution. It would, again, giving you the hint, involve conditioning on the element E2. So in one case, it's working for shear, and the other part of the partition would be that it has failed for shear. So this would give you two simpler configurations, again involving the elements that are mutually independent, 1, 3, 4, and 5. So it would be straightforward to solve those two simpler systems. And this would be the answer. We now see how to handle situations where the same element occurs repeatedly in the reliability block diagram because of its role in system failure or system survival. We just saw one, but let's take up one example from structural engineering, because these things occur frequently in structures. So we start with an example for what is known as a 2 out of 3 redundant system. We are again going to look at this formally later, but this is basically what it means. Recall that the indicator function of element I is xi, so it's 1 if the element is working and 0 otherwise. So we have the system's structure function alpha in terms of the element states. Now, if we are given a 3-element system and the system works as long as at least 2 elements work, that's very important. At least 2 elements work in this, that's why it's called 2 out of 3 systems, or in general m out of n systems. So the structure function can be given simply as 1 if the sum of all the x's is at least 2 or 0 otherwise, or if you want an analytical expression, it's quite clever. It's the expression that you see on the bottom of your screen. What would be the reliability block diagram of such a system? So it could, if you want to go through all the possible combinations, this is what it would look like. So since at least 2 have to work, it's E1, E2 have to be in series, or E2, E3 have to be in series, or E3, E1 have to be in series. And this obviously includes the case when all 3 of them are working as well. There's a more concise way of expressing this, and that would be we just put a block there called 2 out of 3, and we pass E1, E2, and E3 through them. So this is the truss that we would like to analyze. This has 6 elements, 2 diagonals, elements 5 and 6, simply supported at A and B. A is a hinged support and B is a roller support. So we need to draw the RBD of the truss. Again, depending on our understanding of the structure and how its boundary conditions are, what its material is, and so on, we can find its reliability block diagram by inspection, or we might have to do some structural analysis as well. So here by inspection we know that this is 1 degree redundant, but suppose we wanted to verify this by analyzing the structure. And let's say, as we have said here, it's elastic brittle. So we could take up the stiffness method of analysis. There are 8 degrees of freedom in all, 2 each at A, B, C, and D, and obviously we need to restrict some of them, and because of the boundary conditions here at A and B, so we would restrict 3 of them. The rank of the global stiffness matrix is 5, so we remove 3 degrees of freedom, and we have the reduced stiffness matrix, and we can invert that and solve the structure. So the point here is that the structure is stable when we have this configuration. There are various ways in which we can, as we remove members, as the structure gets damaged, there are various ways of finding if the structure has collapsed, has become unstable or not. We can just, for this simple example, we can see when the stiffness matrix no longer remains invertible. So let's remove one member. Say let's remove member 1, and we can see that the structure is still stable, and we can invert this and we can get answers. So if member 1 is removed, the structure still has not failed, which confirms our understanding of the degree of static indeterminacy for this structure. If we remove one more member, the structure no longer remains stable, so the structure has failed. So if we do this again and again for various combinations pairwise for lost elements, we will see that any 5 have to work. Any 5 of these 6 elements have to work. So we could draw an RBD and say that there are 6 elements, E1 through E6, and 5 out of 6 configuration, which when expanded looks like this. There are 6 ways of choosing 5 elements from the group of 6. So this would be the expanded form of the reliability block diagram of the square truss in question that has 2 diagonal elements.